Okay, thank you, Shair. Thank you, Ramaj, also for the organization of the workshop. So I will start this training workshop devoted to machine learning for economic analysis. So if you have some question, don't hesitate to use to ask your question directly or to use the chat. I use here the chat. Okay. So let's go. So first slide is presentation, but the presentation has been done by Shair and myself. Just if you want more information about my research or my personal website, you can click here on my Google Scholar page or personal website. So first, let me start with training objectives and outlines. So the objective of the webinar is to train participants in the main machine learning methods. Okay, so we'll make a focus on supervised classification and regression techniques. Okay, I will define the term in a few minutes. And the idea is to propose a first introduction to basic method in machine learning for regression and classification, and to introduce also a reflection on the existence of a trade-off between the interpretability and the predictive performance of this of the models derived from ML algorithm. So the course is based on neural knowledge, on probability and statistics, as well as basic knowledge of programming. I will discuss this point later. We'll use Python, but okay, this is not a problem if you don't have some notion with Python at this stage. But most important is the fact that I consider that you don't have any knowledge in machine learning. So I heard that some of you have already followed some machine learning lecture or use machine learning in their research. So I guess that you have some knowledge in general definition, in some particular machine learning algorithm, but I will assume that most of you don't have any knowledge about machine learning. That's why I will begin by defining all the terminology or the terms that we generally use in machine learning and AI, and while assuming that you have no particular knowledge on this point. So the outline of the webinar is slightly modified with respect to the syllabus that I send you, because I guess that in 4 days I will not have the time to teach all the elements that were specified, but this is just repackaging of most of the elements of the syllabus. So we have 4 parts. In the first, I will start with the definition and basic concept of machine learning. As I previously mentioned, I consider that you don't have any knowledge in machine learning, and so I start by defining the terminology, defining the basic concept of machine learning. Here we will discuss difference with artificial intelligence, the different notions of machine learning, of learnings method, and the main machine learning algorithm. And then in the second part, we will focus on the implementation of ML models. So I will not enter into detail in some particular machine learning models at this stage, and just discuss if you have a machine learning algorithm, machine learning model, I will define the difference, how to implement it. And so we'll discuss bias, variance, complexity trade-off, the crucial issue of overfitting, the crucial issue of fixation of hyperparameters, and the cross-validation techniques. Then I will focus on different types of machine learning algorithm. First, I will introduce you the decision trees. So decision trees for regression, decision tree for classification. I will insist a lot on the decision tree. Why? Because the ensemble methods that I will present here are based on the decision tree. So if you don't have in mind what is a decision tree, it is difficult to explain you what is a random forest, for instance. So we will present you the principle of binary division, the CART algorithm, what is impurity measurement, the pro-streaming, the pre-streaming methods. And then in last part, we will discuss, we present you what we call the ensemble method, and especially the bagging and a particular case of bagging, which are the random forest. And if I have time, the boosting with the AdaBoost algorithm or the XGBoost algorithm. I'm not sure to have the time to present you the boosting techniques. It will depend on the speed in which we will discuss together on the bagging and random forest. So what we will and what won't do. So what we'll do together. There are many ways to teach machine learning, depending on the professor. For instance, I can teach you a lot of methods, of algorithm, random forest, super vector machine, deep learning, what you want. And just in few time, I just show you the general idea and the scikit-learn package to implement it. But here I prefer to adopt another approach that consists in presenting a limited number of methods, which are often used in economics and finance, and to present them in detail. Okay. So the objective is to well understand the advantage and limitation of these models, and to well understand the Python procedure to implement them, and the possibility for you to analyze and interpret the results provided by these Python procedures. So what we won't do together, I will not present you an exhaustive overview of machine learning algorithms because I will focus on few of them. We won't go too far in formalizing ML method because it could be difficult, but sometime I will have to present some mathematical or statistical foundations of some methods, especially for the bootstrap. For the bagging and boosting method. We won't go into detail about the preparation of the data used for this algorithm. So I will not discuss with you how to prepare the data, how, for instance, to discretize or to to transform your categorical variable into dummy variable, or to discretize the continuous variable, or to the discussion about the standardization, normalization of the variable, because I don't have time to discuss the preparation of the data, what we call a feature engineering or data engineering, that constitutes the phases before the implementation of the machine learning algorithm. We don't process unstructured data, so image, text, and video are not considered here. The only type of data that we consider are tabular data, NiveUseX file, for instance, XLX file, for instance. So all the application will be done with Python, and we will use Python on Colab. So Colab is a service provided by Google. Google Colab, for short for Google Collaboratory, is a free cloud-based platform that allow you to write and execute Python code in a browser environment. Okay, so you have the possibility to host what we call a Jupyter Notebook service, and we will use this service. So the link is here, and to use this this service, you just need to have a Google account. Okay, so I think that we will start to go to Google Colab. So just to show you how to go to Google Colab here. This is the logo of Google Colab. And so you just have to be logged in and with your Google account, okay? So I think that we will use Colab maybe tomorrow or next week, okay? For the bibliography, for the references, I recommend you 3 books, depending on what you want to do in general. So if you want to learn the statistical foundation of machine learning, the Bible is a book by Askier, Rani, and Friedman. So the element of statistical learning, so this book, okay, you have no application, but you have the mathematical foundation or statistical foundation of what the main method, main algorithm used in machine learning. On the opposite side, you have here a book that I recommend to you if you want to implement your machine learning model or method with Python, and specifically with scikit-learn, which is a package devoted to machine learning provided by French research department INRIA, and TensorFlow for deep learning and massive data. So this is a book for Python. This is a book for the mathematics of the statistical theory. And you have also here a book that I recommend to you if you just want to understand the advantage for the economic analysis of the main machine learning algorithm. So there is no mathematical discussion. There is no implementation with Python. There is just a discussion about the advantages and limits for the use of some machine learning algorithm in economics and finance. This book has been written by Yule, who is the author of the main Bible of the pricing for option and so on, etc. So the title of this book is Machine Learning in Business: An Introduction to the World of Data Science, and I recommend you this book. Okay, so let me start with ML definitions and basic concepts. Okay, so the objectives are to introduce the definition of the term artificial intelligence, machine learning, deep learning, NLP, so natural language processing, and to understand the difference between what we call a supervised, semi-supervised, unsupervised learning, and to well understand the difference between what is an algorithm and what is a model in machine learning. Okay. Okay, let me start with general definition of artificial intelligence. So AI is a field of computer science, okay, so which is focused on creating intelligent machines that can perform tasks typically requiring human-like thinking. Okay, so it's a very, very general definition, but I think that you will understand the difference with machine learning, a process using algorithm rather than procedural coding that learns from existing data in order to predict future outcome. So broadly speaking, it is a field of computer science that deal with the development of models whose parameters are estimated automatically from data with limited or no human intervention. There are many terms in this definition. What are the most important terms? So first, so broadly speaking, okay, machine learning deals with the development of models. Okay, so we have some models. So you know what is an econometric model. For instance, the linear regression model is a model. Okay, so in machine learning, we have also the development. We are also interested by the development of models. These models are generally used to predict future outcomes. So it's the main usage of machine learning is a forecast. It's to forecast. Okay, it's a forecasting issue. I noted that Mireille Maher was interested by causal machine learning. This is a new trend of research in machine learning with the work of Esther Duflo, etc. But most of the usage of the current usage of machine learning in general, not in economics and finance, but in general, is to build some forecasting model. Okay, this is not a causal model. Okay, this is just a few usage of machine learning in general. These models have some parameters, okay, as in standard parametric models. And these parameters are estimated automatically, okay? And just, this is not only a question of estimation, this is also a question of specification. These models are automatically specified, okay? With limited or no human intervention. And this is the main difference with econometrics, because in econometrics, you have an economist that who specifies the form, the functional form of his model. For instance, I have a linear regression model. I will introduce the GDP and the inflation rate and the unemployment rate in my equation as explanatory variable to explain, for instance, the interest rate, okay? Here, the specification, linear or not, the choice of the explanatory variables, okay, will be automatically defined, automatically down by an algorithm. This is the main difference between machine learning and econometrics, okay? In econometrics, we have econometrician choose, specifies its model, his or her model. In machine learning, this is an algorithm that specifies the model, okay? And so the parameter, the specification is deduced from the data. So in general, ML and AI are often confused, but okay, you just have to understand that ML is a subfield of AI, okay? So we have this type of graph. So we have computer science, a subfield is AI, and the subfield of AI is machine learning, okay? And within machine learning, we have four different type of learning, okay? We have the supervised learning, the unsupervised learning, the semi-supervised learning, and reinforcement learning. I will not discuss here what is self-supervised learning, okay? And we have also a very specific part of machine learning, which is deep learning, okay? So we have to understand all these terms. So before to define these terms, I have to introduce some vocabulary. So in general, in machine learning, we consider an experiment, okay? This is a name in machine learning, and this corresponds to a set of data extracted for the observation of a phenomenon. So this is your Excel file, okay? Okay, this is your data set. Your data set will be decomposed in different parts, and the most important part in what we call the training data set, okay? So it corresponds to your estimation sample in econometrics, okay? This is a data set used to train or to estimate the model. So in general, in econometrics, we say to estimate the model, okay? But in machine learning, we say to train a model, okay? Just the difference, and okay, the idea is that, okay, in general, in econometrics, you specify the model, you say, okay, y is equal to a1 times x1 plus a2 times x2, okay, where x1 is unemployment, x2 is GDP, okay, and you just ask to your software, for instance, R or Stata, to estimate the parameters a1 and a2. So you specify and the software estimates. With machine learning, the software Python will both specify and estimate the parameter. And that's why we use the terminology to train a model, okay, and not to estimate a model. The sample that you use to train your model has some elements, and all these elements correspond to example or instance, okay? Two terms. So, for instance, typically typical example, you have an example x1, example x2, example, okay? So this corresponds to your firms, to your individuals, to your assets in your data set, okay? So you observe, for instance, n firms, n data set, n assets, or n what you want to n countries. Each country corresponds to an example or an instance. This corresponds to your individuals in the econometrics. For each individual, so for each example, each instance, we observe the explanatory variables and the dependent variable. I use so econometric vocabulary to make use the link between the econometric vocabulary and machine learning vocabulary. In machine learning, the explanatory variables are called the feature, model features. And the dependent variable, y, is called the target variable, okay? So, if I summarize, in a typical data set, you have some examples, you have some features, and you have your target, okay? Y, the feature X, and each line is an instance or an example, and you have, okay, feature rows, colon, and okay, here you have your Y series, and the Y series, so the target variable, has some label. So what we call a label is simply the value of the target variable, okay? So here we observe the label, so it corresponds to the value of the Y dependent variable, okay? So let me go back to the different types of learning modes in machine learning. So I distinguished supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. The main difference between these types of learning is related to the fact that the dependent variable, so the target variable, is labeled or not. What does it mean? It means if you observe or not the value of y. So, a supervised learning aims to detect an explanatory or predictive model on labeled data. Okay? So you have data, a data set in which you observe y. And here you can do a regression model if y is continuous, or you can do a classification model if y is discrete. On the opposite, you have an unsupervised learning. And unsupervised learning is based on the use of unlabeled data. So unlabeled data means that you don't observe the values of y, of your target variable. So I only have x value. I only observe the feature, the model feature. And what is the main objective of unsupervised learning algorithm? There are many types, but okay, in general, these algorithms are devoted to two types of questions. The first is a clustering, and the second is a dimensionality reduction. Okay, so clustering, it consists in grouping the individual, so the instance, into groups, okay, of individuals who have approximately the same type of behavior. And the dimensionality reduction is the same idea because, okay, if I have a cluster or if I have a group of variables, I try to identify a main factor that represent most of the variance of the other variables. Okay, we'll discuss this point later. The semi-supervised learning is the learning type which is based both on labeled and unlabeled data. Okay, I will discuss this point later. Okay, for instance, let's just imagine a fraud detection model. You have some fraud data sets, a fraud data set in which you observe fraud or no fraud for a set of firms that have been controlled. And for all the firms that have not been controlled yet, you don't observe if there is a fraud or not. Okay, so you have a mix of labeled and unlabeled data. Okay, so it's enabled learning, and reinforcement learning is very particular because, okay, you have in which the algorithm receives some feedback from data and guides the user towards the best result. It is used more and more in finance. I noted that sorry for I lost the name. Amir Lanoir use machine learning for portfolio allocation, and more the type of learning that it is used in portfolio management is a reinforcement learning. Okay, but today, unfortunately for Amir, we will focus on the supervised learning. Okay, so if I summarize, supervised learning, semi-supervised for labeled and unlabeled data, if there is a mix, and reinforcement learning is very specific. Let me learning algorithm works. So the algorithm learns from a training data set containing labeled data. So data that are already labeled with the correct label. So for instance, Y, so I observe Y. And the algorithm tends to produce a general rule, so a model for the classification or for the regression, which is then used to predict label, to predict Y, with when new data is analyzed. Okay, so you have an algorithm. Okay, an algorithm that generates from the data. Okay, a model. Okay, and if I use new data, this model generates some forecast. Okay. Sorry, I have a problem. It's clear? Okay. Let me illustrate this point. Let me consider an example in which we have a set of images. So this is our data, which are labeled. Okay. So we have some images and we have a label Y that is equal to 1 if it is an apple, 2 if it's a citrus, 3 if a watermelon, and 4 for a banana. Okay. So each we have a training set here in which we have some images of fruits, and for each images of fruits we have a label 1, 2, 3, or 4. Then for each image we have also a set of features. So the features are represented by a vector. Okay, here. So this is a X and this is a Y here. And for instance, we measure the color of the fruit, the shape of the fruit, okay? And this, okay, data are presented in the form of vectors, okay? So we have a data set, okay? We have Y. So for instance, 1 for the first instance, 3 for the second instance, 4, etc. And X, which is a color, for instance, red, okay, yellow, green, okay, and the shape, etc., the weight, for instance, 10, okay, 12, 10, etc. Okay. This data set, this training data set, is introduced in an algorithm. What is an algorithm? It's a kind of code, okay, a sequence of program, okay, that will generate a model. Okay, so a model is a functional form Y, which is equal of a function f or h of x. Do you have an equation for this model? No. Do you have a graphical representation of this model? No. This is a kind of implicit model. If I enter X vector, then I will obtain a forecast Y hat. Okay. So this model now can be used in a new data set, which is different from the training data set, which we call the test data set, in which we have some images, some new images of fruits that have not been used during the training of the model. And then, given the X, so the feature of this data set, we will predict the label Y for these two images. And we say, okay, the model predicts, for instance, that these images correspond to watermelon, these images correspond to a citrus, and etc., etc. This is clear? So we have, as terminology, we have a training data set, a test data set, you have the model feature, and you have an algorithm. This algorithm produces a model or predictive model, and this model is used to make some forecast of the label of the new data that are in the data set, the test data set. Do you have some question? No? Okay, don't hesitate. Yes?
I have a question here. So it's like we are in the econometric language, we are just like estimating a fixed effect model with no variables at all.
No, you have the variable here, which are the feature, which correspond to the explanatory variable of your model. The main difference is that you don't have a formal equation. Okay, you don't have, for instance, y is not equal to 0.8 times x1, etc. You don't have an equation. You don't have even a graphical representation of your model. Okay, you just have a functional form. If you enter x1, x2, x3, okay, then you get a forecast y hat. Okay.
Yes.
Because this is a second difference with econometrics. In econometrics, you specify. I say that okay. First difference in econometrics, you specify your model. You say okay, I will use among the feature. You will use a color. Okay, I will use a weight, but I will not use a shape. Okay, so the first difference with machine learning is that the algorithm will select by itself the different features that you will incorporate in the model. For instance, if you have x1, x2, x3, x4, we have, for instance, 4 features in my data set. The algorithm will select, for instance, x2, x4 in the model, okay, and not x3 and x1. So there is a kind of automatic selection procedure. And this is, in econometrics, we have some variable selection procedure, such as set, for instance, in linear regression model, maybe you know what is a stepwise or backward selection procedure model. You have a set of variables, and then this algorithm select the variable in your model. Okay, this is the same idea, okay? But more fundamentally, the specification, so the form of the model, is also specified by the algorithm. Okay, and maybe sometimes, for instance, there is no reason that the algorithm will choose a linear, in general, this is a non-linear specification of the model that is selected by the algorithm. Okay, the form of the model depends on the type of the algorithm. If I use a support vector machine, I will have a type of model. If I use a random forest, I will have another type of model, etc., etc. Okay, and at the end, I have no idea of the form of the model. And this is what we call sometimes a black box model, in the sense that, okay, I don't have any idea of how the model here, which is here, works. Yes, Fatime?
Excuse me, like in structural models, we can run counterfactuals after estimating the model. But can we do this in this environment? Can we estimate the model and then run counterfactuals to evaluate policies ex ante?
The counterfactuals can be used to, if I well understand your question, is to know if counterfactual can be used to understand how the model works. It is your question?
Yes, sometimes
Yes.
we want to evaluate a policy before implementing it. So
Yes.
we use counterfactual analysis when we estimate a model. Can we do that in this environment?
Yes, yes. So you run, because, okay, to make a counterfactual, it's to make a forecast of what it could be happen if we neglect a factor, okay? So
Okay.
it's just a forecast, a counterfactual analysis. It's a particular forecast, but it is a forecast. So you can use a list of factors of vector of explanatory variable, what you want. Neglect the policies that you want to evaluate and to consider a counterfactual, and then to run to ask to your algorithm to select a model to predict the effect of your treatment, for instance, in counterfactual cases in which you neglect the impact of a particular policy. So it can be used, machine learning can be used to produce counterfactual analysis. Yes.
Thank you. But it's in this sense that I have to eliminate a specific variable. Am I right?
Yes, exactly.
Yes. Thank
And
you.
you have be careful because you have to eliminate physically in the data set. Okay. Because if I send my data set this variable, I'm not sure that the algorithm will select it or not. So I have to delete by myself before to send it to the algorithm. Yes.
Yes.
Yes, Samal.
Hello, all is clear so far, but I just want to make sure that I understood clearly related to the model. You said that in this case, the model cannot be something like y is equal alpha plus beta 1 x1 plus beta 2 x2. In this case, since in economics we define the model and then we start, how should we start in this case?
How do we start? Do we understand the way the model is working? This is your question, yes?
Yes.
Yes. Okay. So it depends. There are two types of machine learning model: white box and black box. White box is the fact that the model is relatively simple. And for instance, this is the case for the decision trees that we will see in a few minutes. Okay. And so you can understand the structure of the model and you can understand why the model take a decision, for instance, 1 or 0 if it is a binary classification problem. Okay. So it isn't possible to understand how the model works. But for most of the machine learning algorithm, for instance, random forest, XGBoost, all the ensemble method and deep learning, what you want, for most of the algorithm, we have a black box model. What does it mean? It means that, okay, here, the model is too complex to understand how it works, okay? And we have no idea of the link between X and Y. I can use my model, introduce X and get a Y result, but I don't understand how the model works. And in this case, you have some method, what we call interpretable machine learning, IML, or XAI, X for interpretable, okay. Interpretable machine learning or XAI, which are some methods that allow you to understand how the model works, okay, to understand ex post what is the structure of F.
Okay, clear. Thank you.
Okay. Okay, so we have an algorithm and we have a model and make the distinction between the two. Huh? Okay, for instance, data for supervised learning or regression, we can have some machine learning algorithm for regression and other for classification. What is the difference in the case in which Y is is continuous, we have a regression model. And in the case where y is binary, for instance, 0, 1, or discrete, 1, 2, 3, then we have a classification problem. So we have algorithm for supervised learning, algorithm for classification, supervised learning for regression. Okay, so regression, classification, this is, for instance, we have two features, x1 and x2, and then we have here some observation y, which are labeled with a plus, other which are labeled with a minus, so 0 and 1, for instance. And then you try to find the hyperspace, so the separation with the decision boundary. Depending on x1 and x2, that allows you to forecast what will be the value of y for the new data, for instance, for a test set. Okay. Supervised learning, when you have a statistical definition. So in general, the supervised learning consists in choosing a function or hypothesis. So this is my model F. Okay, here in general in machine learning, which this is an hypothesis or a function. Okay, H that best predicts the observation in the space of functional hypothesis. In case of the classification, the hypothesis, so the model. Okay, and so don't be perturbed by the vocabulary. Okay, the function, the hypothesis correspond to what we call in econometrics a model. Okay, just a question of vocabulary. If you have a classification problem, the hypothesis, so the model, correspond to a classifier. If you have a regression, the hypothesis or the model correspond to a regression model. The model is trained on a training sample. And the model is assessed, so it's evaluated. For instance, if I have to compute my R-squared, if I have to compute my IUC for a classification model, etc., I use a second sample, which is called a test sample. Okay. So let me start with the first way to proceed to machine learning. The first action that you have to do is to split your data into train and test. For a test set, you don't use your test set to train or to estimate your model. You train your model only on the training set. In general, the training set represents 70% of the observations, and the test set represent, for instance, 30%. It's not a general rule, okay, but it is a rule of thumb. Then, with a training set, you apply an algorithm, and this algorithm will build and fit a model. Okay, so you have a model here, and this model will be used on the test set that have not been used for train the model. And then, given you will test or assess the validity of your model by producing some prediction on the test set by using this model, and you will compare this prediction to the true labels, to the true y. Okay, so you have prediction y hat, and you have the true label y, because on the test set, you observe y. Okay, here you observe y, and here you observe y. And you will compare y hat to y to evaluate the performance. For instance, you will compute the R-squared or the MSE, the mean square error, or what you want for a regression, or the IUC, or percentage of correct classification if you are in a classification problem. It's clear for you? This is new compared to econometrics, because in general, in econometrics, we didn't separate or split your data set in the first stage of your analysis. Okay. Let me say a few words about the other type of learning, which are not in in the topic of this webinar, but okay, just for your culture, for unsupervised learning first. So unsupervised learning, you have unlabeled data. So there is no longer variable to predict, okay? Because, okay, you don't observe Y, so the question is not to predict Y, okay? Then, in general, the algorithm of unsupervised learning look for regularities or association rules in the data to identify groups of similar observation. So, for instance, some clusters. And the main problems addressed by unsupervised learning are clustering and dimension reduction, for instance, the famous PCA method. Okay, let me illustrate. Okay, in this case, so we have a training set and a test set, and you have some images of fruits, but in this case, we have no label. So we don't say this is a citrus, we don't say this is a watermelon, we don't say, etc., this is a banana, etc. So we don't put a label on the data. So we don't observe Y, we have only the X vector, okay? So for each image, we have the shape, the color, what you want. And then we use a machine learning algorithm to produce some cluster. So to group the individuals of the training set, given then their similarities. For instance, okay, the model will produce a cluster of the fruit images that are yellow. It will produce the fruit images with leaves. It will put another cluster in which there is only watermelons. Okay, so there is some cluster of images given their characteristics, so the weight, the shape, etc. Okay, we have. This is not truly a predictive model, okay, but this is a model that relate for a new set. If I introduce a new images, I observe the X, and then given the X of the feature of my images, of my instance in my test set, then these individuals will be affected to this cluster. These two individuals will be affected to this cluster. And these two images will be affected to the third cluster. So in that sense, the model, the unsupervised learning algorithm produce a kind of model that relates the feature, okay, a group that depend on X. Give me your age, your salary, etc. I will give you the cluster that you belong to. Okay, this is the idea of the unsupervised learning for the clustering. Okay, the dimensionality reduction is about the same idea. Do you have any question about that? Great. So, for instance, most well-known, best known clustering algorithm is a K-means. Okay, that minimize the variance within each cluster and maximizing the variance between the cluster, but we have many other algorithms for clustering in machine learning. Okay, but the idea is to, for instance, we have X1, X2, and we group all these units here in a cluster, all these units here in a second cluster. And if I have a new data, given X1 and X2, I will affect a new data here to the first cluster or to the second cluster. Okay, this is the idea. Semi-supervised learning. So we have a mixed between with in your data set. So you have some label data, usually in the minority. Okay, so you have few label data, and you have also unlabeled data, usually in the majority. Okay, So let me illustrate here. I have a small amount of label data, so individual for which I observe Y, and a large amount of unlabeled data set. Okay, for instance, I gave you the example of a fraud detection model. So I made some control on a few set of firms. So I observe Y is equal to 0, Y is equal to 1 for all these firms. And I have a large set of firms which has not been controlled yet. And then I don't know if they are made a fraud or not. And then you can use a semi-supervised machine learning models. And the semi-supervised machine learning model will produce a forecast for all the individuals. So here you have your label data. The label does not change. But here you have the unlabeled data for which the algorithm will produce what we call a pseudo label. So this is what is a pseudo label? This is simply a forecast on the value of Y. Okay, so we will the model will forecast if this firm has made a fraud or not. So if Y is equal to 1 or Y is equal to 0. This is the same for this firm, etc. I gave you an example of classification, but this is the same for regression. For instance, if the unobserved amount of, I don't know, of the, this is an unobserved amount of salary of what you want, then my model is able to affect a pseudo label for all the individual, for all the instance for which I do not observe the value of Y. Okay. This is why the semi-supervised learning methods are used to give pseudo label. And then this is an iterative approach. In general, we use this pseudo label data set to the model to train the model, and then we have a retroaction. Okay, until there is a convergence to say, okay, we are sure that we are forecasting the label in a good way. Okay. Do you have any question about semi-supervised learning? No. Last type of learning is a reinforcement learning. Okay, so this is a behavioral learning model in which the algorithm receives some feedbacks from data analysis and guides the user towards the best result. So for instance, so in general, it was used, for instance, in gaming. Okay, you have the player make an action, and there is a feedback from the environment of the game, and then there is learning, behavioral learning that change the way to decide your actions. Okay. In general, it was very rarely used in economics, but as I said in my introduction, there is a growing interest in finance, okay, for the reinforcement learning. But to my point of view, this is the only type of economics in which, or field of economics in which the reinforcement learning is used. Okay, and the reinforcement learning is based on the idea of a reward and a state and the policy and action. Okay, other form of learning. So deep learning is a subcategory of ML that refers to specific methods that integrate neural networks in successive layers to learn data iteratively. Okay, why I didn't discuss deep learning in detail, because the usefulness of deep learning for tabular data is particularly discussed. It is true, there is no doubt that deep learning is particularly useful for textual data, for image, for video, etc. But for tabular data, for an Excel file, in general, most of the time, There is no gain, accuracy gain, or precision gain, for instance, from R-square compared, for instance, to ensemble method. That's why, okay, I consider that it's not the topic of his main topic of this training. And the other type of learning is natural language processing, which is specifically devoted to textual data. So the PDF, for instance, okay, and to use the text. And okay, combined with some processing techniques, these tools can also be used to analyze voice data. Okay, so this is very particular. So we have artificial intelligence, a subfield which is machine learning, and a subfield of machine learning which is deep learning, because it is a type of algorithm which is based on a particular type of algorithm that rely on neural networks. Okay. So let me summarize. We have the computer science, artificial intelligence, machine learning, which is a subfield of artificial intelligence. And in machine learning, you know what is supervised learning, unsupervised learning, semi-supervised learning, reinforcement learning, which are the four main type of learning in machine learning. The deep learning, which is a type of machine learning based on a particular algorithm that are the neural networks, and this is a subfield of the algorithm based on neural network in machine learning. And self-supervised learning is out the scope of my presentation. Do you have any question about the definitions? No. This is another presentation by IBM. So artificial intelligence, machine learning, supervised, unsupervised, reinforcement, deep learning. And here you have NLP, reasoning, which is another type. So now we know that there are many types of different type of learning in machine learning. So, and which algorithm are most widely used in economics and finance? This is a difficult question. So let me first give you an overview of the type of algorithm generally used in machine learning in general, not in economics and finance, but in machine learning. So I used two different presentations. On the right, this presentation comes from scikit-learn, and on the left from another source. So in machine learning, we distinguish the type of learning, I said before. And for the supervised learning on the left, you have the classification and regression. Okay. For the classification, let me start with the linear with the regression. Okay, let me start with supervised learning and regression algorithm. The first algorithm that you will find in a book of machine learning is linear regression. It is a little bit tricky because I said that, okay, be careful, because it is not the linear regression as you have in mind, because there is also a selection method to select which are the variables that are introduced in your linear regression model, okay? But you find the linear regression model. You will find the neural networks regression, a support vector regression, the decision tree regression, and some penalized regression like lasso regression, ridge regression, etc. So today, unfortunately, I don't, during this webinar, I will not have the time to present you the different, but I will focus on the decision tree. For the classification, you will find the decision tree, the support vector machine, random forests. Random forest can also, this is a typo here because, okay, the random forest can also be an algorithm for regression. The random forest can be used for regression, but also for classification, okay? And I will present you what is a random forest. For other, for unsupervised learning, okay, you have clustering method, mainly clustering method, and the most well-known is K-means. It's not necessary to discuss the name of the other method. Reinforcement learning, okay, Q-learning, R learning, TD learning, whatever. Let me focus on the right on this other presentation. This other presentation is interesting because, okay, this is not the same presentation as here, depending on the type of learning. We have the machine learning, and here, the author of this presentation distinguish first the classical learning. We have classification, regression, clustering, pattern search. Okay, so we have here supervised learning, here unsupervised learning, okay? And we see the same name of algorithm. So for instance, the linear regression, the ridge lasso, so some penalized regression. Here you find the decision tree, whatever, okay? The k-means here. We have the reinforcement learning. Okay, this is particular. And here we have another set, which is the ensemble methods. The ensemble method is a way, what is an ensemble method? Is a way to aggregate an individual classifier. So I have, for instance, a regression, and in an ensemble method, I will aggregate several models to make a better forecast. Okay, in general, this is not a regression model that we aggregate, but we will see that, okay, this is a way to aggregate some what we call weak learner to obtain what we call a long or a strong learner, so better learner, and we'll discuss why. And here you have two main approaches, bagging and boosting. And in the bagging, the main algorithm is a random forest, okay? So let me clarify what we will do together. We will explain what is a decision tree. A decision tree can be used to do regression or classification, whatever. And then I will do not present all other type of algorithm in supervised learning, okay? Because there are plenty of them. I will focus on what we call the ensemble method, and I will discuss with you the bagging with a random forest, and if I have some time, the boosting. And I will discuss here the famous XGBoost algorithm. Okay? This is another table of okay, for the type of algorithm. Okay. This is not just at this stage an overview of the algorithm, but which algorithm are used most frequently? This is a difficult question, okay? So you can find on LinkedIn or whatever some sources in which are kind of top 10 machine learning algorithm used, etc., etc. Or I can send you different presentation, okay, but on this point, but okay, let me summarize to be brief. In general, okay, the most often used algorithm are logistic regression, which is not machine learning for me, it's just an econometric model, okay. But in general, we find the decision tree, the neural network, and the super vector machine. But okay, today what we find are here in general are the ensemble method, and especially the bagging, so the random forest, and the boosting method with AdaBoost and gradient boosting tree, so XGBoost. Okay, why? Because it is well known that this method gives you the better forecast, okay, compared to others. That's why what we find here are XGBoost and random forest and decision tree. Do you have any question? So let me summarize. We have seen what is artificial intelligence, what is machine learning, the type of machine learning modes, so supervised learning, unsupervised learning, semi-supervised, reinforcement learning, the type of learning classification of regression, the difference between what is an algorithm, what is a model, and the NLP. Any question? Okay, I propose maybe to make a break of 10 minutes. Do you agree before to start the section 2?
Yes, we do.
Okay. So a short break of 10 minutes. Okay. So if everybody is online, I will start with the second section. And it's devoted to the implementation of ML models. What is the idea? The idea is, okay, before to presenting you a particular ML algorithm, whatever, decision tree, random forest, XGBoost, whatever, I propose to introduce some general principle to on how implement ML algorithm, okay? And we will discuss critical issues of overfitting and the general principle of cross-validation of the hyperparameters, okay? So this is a general discussion. We do not detail a particular algorithm, but we just discuss general principles on how to implement a ML algorithm. So what are the specific issues with ML algorithm, whatever the type of ML algorithm? The main particular issue is trade-off that exists between the bias and the variance of your model, okay, of your hypothesis. And this trade-off is also related to the complexity of your model, okay? We discuss this point. And this trade-off has a strong consequences of what we call an overfitting issue. The fact that your model is good in sample, so on the training data set, your model has a very high level R-squared or high IUC, whatever, and is poor, its performance is poor out of samples on the test set, okay? And this is particularly problematic for a forecasting model because it corresponds to a lack of generalization. So your model is not able to provide good forecast for new data on which it has not been trained. So this is a way to control for this overfitting issue is to choose some optimal values for the hyperparameters. And for that, we will use a cross-validation technique. I will not discuss the unbalanced sample, sorry, this is a typo. Okay, so let me start with bias variance complexity trade-off. So I have to define the notion of bias, the notion of variance, the notion of complexity, and to understand the trade-off between these two dimensions. Okay, so let me start with a world in which we assume that there is a real relationship. So this is a data generating process between y and x. And let us imagine that, okay, yi is equal to f of xi plus epsilon I. And f here corresponds to the true model, okay? Which by design is unobservable. So you have a training data set. So this is a collection of x1, y1, xn, yn. And given this training data set, you train a model, so an hypothesis in the ML vocabulary, f hat of xi. And we want to decompose the expected squared error on the test set. Okay, so this is not the idea to decompose the error on the train set, but on the test set, so for new data. Okay, and we want to decompose this quantity. So we want to compute this quantity. So the expectation, the mean of the squared of the difference between f hat minus y for x that belongs to the test set. So the bias, the model bias, is the difference between the expected value of the prediction and the expected value of the true model. Okay, so the bias is simply the mean on a given sample, typically on the test set, of the difference between f hat minus f of x. Okay, so as a mean, the expectation is a linear operator. This is the difference between the expectation of f hat minus the expectation of fx, and we epsilon e in index d denotes the expectation with respect to the test sample dataset. Okay, so we just to be clear, we want to compute the mean, but with the data that belong to the dataset. Okay. A model with a high bias gives very little weight to the training sample data and oversimplifies the model. Okay, it always leads to high error on the training and test set. Now, what is the variance? So the variance measures the dispersion of the model prediction. Okay, so we have some sensitivity to the fluctuation in the training sample data set. So, okay, we have variability, and then the variance of the model corresponds to the variance of f hat. Okay, the variance is also defined on the test set. So this is, you know what is the definition of the variance. This is the expectation of the difference between y, the squared difference between y and the expectation of y. This is the same here. You have the f hat minus the expectation of f hat, the squared here, and you consider the expectation of this quantity. Okay, so what are the idea of low variance, high variance, low bias, high bias model? Okay, let us imagine that, okay, we have here a target, and here you have the y hat forecast. Then when you have low variance and low bias, your prediction, your forecast are concentrated around the true value of y. A model with a low bias but a high variance means that, okay, on average, your forecasts are good because they are close to the true value of the expectation of the y, but the variance, the dispersion of your prediction is large. Okay. Well, a model with a high bias and low variance means that, okay, you have a small dispersion of your forecast, but your forecasts are not close, are far from the true value that you want to forecast. Okay, and the worst estimator or model is a model with high variance and high bias, because, okay, not only your predictions, your forecasts have a high variance, but they are also far from the true value. Okay, what we call an overfitting issue. An overfitting issue corresponds to this case, corresponds to a model that has a low bias but a high variance on the test set, that is on the new data. Okay? Let me explain. For that, let me decompose the expected squared error as follows. So here you have the total error, the total squared error. That is the expectation of the squared of f hat minus y. It is possible to rewrite this quantity as follows. Here, you can define the squared of the bias. Okay. Here, you have the squared of the difference between the expectation of f hat minus the expectation of y. I consider that here that y is observed, so I skip the expectation here, plus the variance of your model, so the variance of f hat plus an unreducible error, so the error of here the variance here of the error term in the DGP, okay, in the data generating process. So when I have a model, I always can decompose the total error as the bias, the squared bias, plus the variance of my model, plus a variance of the error term. What does it mean? It means that, okay, when I have a large error in my forecast, it can come from the bias or for the variance. And now let me introduce a third term, which is a model complexity. And let us imagine that I have a model which is very, very, very complex. Okay, let us imagine, for instance, a polynomial regression with many terms. In general, we observe that the bias of the model will be low. What does it mean? It means that on my training sample, I will have a very high R squared. But on general, when I use this very, very complex model on new data, this model is not able to generalize to new data. And when I compute, for instance, the R squared on a test set, then I will have a large R squared. And where does it come from? It comes from the fact that, okay, the variance of this complex model tends to be high. So increasing the complexity of the model reduces the bias, but increases the variance of your forecast. On the opposite side, when I consider a very, very simple model, for instance, let us imagine that I consider a linear regression model. A linear regression model, the risk with a linear regression model is the fact that I have a high bias because my model does not capture all the non-linearities in my data set, etc. But when I redo the forecast with the same model on new data set, there is, in general, few variance. And so the variance is low. But what does it mean? It means that when I consider my total error, remind that the total error is the sum of the bias squared plus the variance. If I have a too complex model, I have a high total error due to a high variance. If I consider a model which is too simple, I have also a high total error, but in this case, due to high bias. And the idea of the machine learning is to find an optimal complexity, okay, to minimize the total error by considering a model that has a low bias and a low variance. Okay. Okay. So what is this idea of complexity? So there are many definitions of complexity in machine learning. We can have time complexity, a space complexity, a model complexity. Okay, but I will not have time to discuss all this point. But okay, let me just, you have a table for competition time. Model complexity, let me focus on the model complexity. What we call a model complexity, it often refers to the number of features or the number of terms included in the model, as well whether the model is linear or non-linear. Okay, now let me consider, this is difficult to define the complexity in general because it's very some strong mathematical concepts, the VC by Batnik, etc. And I want to avoid this type. Okay, so let me go back for specific machine learning algorithm, and then it is easier to define what is complexity. Okay, let me at this stage, you don't know many, you don't know none machine learning algorithm, but let me consider that a linear model is a machine learning algorithm. Then what is the complexity? Is simply the number of non-zero parameters. For people who know what is a decision tree is characterized by some leaves and decision nodes. And in a decision tree, the complexity is measured by the depth of the tree, of final leaves that you have in a tree, etc., etc. Let me, okay. So there are some theoretical measures of the model complexity, and the most well-known is a VC dimension by Vapnik and Cherny-O'Keefe, and there is also what we call the Fisher information matrix. You know what is a Fisher information matrix because this is related to the maximum likelihood, okay? But there is a difficulty to make the link between the number of parameters and the computation time complexity, okay? But let me focus just on this idea of model complexity measured by the number of parameters in very simple model. What does it mean? It means that in general, no, that's it. Sorry. So the key concept, the bias of a model, is the expectation difference between expected difference between the forecast of the model and the true value of the series. The variance, it measures the dispersion of the forecast of a model. And what we call the total square error is the sum of three terms: the bias squared, the variance, and the variance of the error term, so irreducible error. There is a bias variance trade-off, okay? Because when I increase, what is the trade-off? This idea is that, okay, if I increase the variance, I reduce the bias. If I reduce the variance, I increase the bias, okay? And the complexity affects not only the bias, but also the variance. And the idea is to find an optimal complexity. Given these definitions, I can now introduce what we call the overfitting issue. So we will define what is a training and test set and define the notion of overfitting. And we will understand the link between the complexity and overfitting and the link with the bias variance trade-off and overfitting. So let me go back to my machine learning algorithm. Okay, and let me split my data set in 2 or 3 samples. First stage, all my available data are partitioned into 2 subsamples. First, the training data set, and then the test data set. In a few minutes, I will have to split the training data set into 2 subsets. Okay, first, what we call the training or proper training data set, used to learn the model, but also validation data set, and we will discuss this point, and this validation will be used to determine the value of the optimal value for the hyperparameters of the model. Okay. What is overfitting? Overfitting refers to a phenomenon where a model performs exceptionally well on the training data, but struggles significantly when presented with new unseen data, so on a test set. In other words, I have a model with a very high R squared on my training data set and I use this model on new data, so a test set, then the R square largely decreases. What is the source of overfitting? Is the fact that the model learns the noise of the specific details present in the training dataset too well. And then it failed to capture the underlying general pattern of the data. Okay? So my model is polluted by the noise in my training dataset and lack of generality of generalization power to new data. Okay, so let me illustrate, for instance, with a regression model. If, sorry, I have a problem. Okay. If you have this type of graph, you will have a very low R squared, but maybe it is the evidence that your model fit too well your training data set. And if I use this model with new data, maybe I will obtain a large decrease in my R square. Okay. Here, if I use this model on my training data set, maybe I will have a low R square. Okay, because this model is not good. It does not capture, for instance, the non-linearity in my data. And okay, I don't want to use this model on new data set because on my trained data set, this model has a low R square, so high bias. And the idea is to find a model like this, which fits well the data on the training data set, but not too well to avoid another fitting issue. I will detail this point in a few minutes. So the problem with the overfitting is the fact that your model has good predictive power on the training sample, but the goodness of it collapses when considering new data, so in a test sample. Overfitting is a common problem with learning model or algorithm. It is a basic problem of all the machine learning algorithms, and it is related to the flexibility of the complexity of your model. Okay, what is the idea? Okay, let me illustrate on this axis. We have the model complexity, high or low, and here you have the prediction error. And the idea, and now I distinguish between the training sample and the test sample. Okay, I compute my prediction error. Okay, for instance, measure my mean of squared error on the train set or the test set. If I increase the complexity of my model, I will always decrease the error, the prediction error on my training set. Always. Okay. The most complex is the better. Okay. Okay. The most complex model is always the better on the training data set because, okay, I will decrease the R squared, for instance, or increase the R squared, or increase the IUC on my training data set because my model will capture all the particularities of my data set. But if I use this model now on the test set, then for a low level of complexity, I will decrease the total error of my prediction. But if I introduce a model which is too complex, then the risk is that the error will tend to increase. And this departure between the error on the test set and on the training set is the evidence of an overfitting issue. Okay? Let me illustrate an overfitting issue. Let me consider a case of regression. Let me imagine that the data generating process, so the true model is the following. We have y is equal to xi squared plus an error term, and the error term has a normal distribution and x has a uniform distribution. Then let me train a model on the training data set, which is simple, a polynomial regression model. Okay. And we will consider a polynomial of degree 1 to 9. Okay, so for enough, it's very simple. I will regress y on x, y on x and x squared, y on x and x squared and x to the power 3, etc. 1 on x1 to the and x to the power 9. Okay, so I have 9 models. The level of flexibility or complexity depends on the order of the polynomial. A model with a polynomial order 9 is more complex than a polynomial model with order 3. We consider 100 observations, 60 for the training sample and 40 for the test set. And we compute the total error on the two samples for all the models. So here you have the order of the polynomial, so it is in French. And here you have the empirical error, so this is an empirical mean square error, okay? What you observe, here you have a training data set and here the test data set. What we observe is the fact that if you increase the order of your polynomial below 2, then you will observe that, okay, the mean square error will increase on the test set, whereas it will decreases on the training data set. Okay. And so the optimal solution or the optimal model here consists in using a polynomial regression of order 2. If I increase to the order of my polynomial, I will decrease my mean square error on the training data set. Okay, I will have a better R squared with a regression with a polynomial degree of order 9 that with a polynomial regression of order 2. But if I use this model on new data, then the risk is the fact that I will have a lower predictive performance. Okay. Let me illustrate. This is the same idea, okay, but with real data. So we want to predict the price of an house depending on the age, okay, of not of the house, but of the house. Sorry. And then here we consider a polynomial regression, and here you have the order of your polynomial regression. It's clear that on the trained data set, you will observe a decrease of the R squared, or an increase of the R squared, or decrease of the mean square error if you increase the order of your polynomial regression. Why? Because, okay, your model will capture all the specificities, okay, of the in sample, okay? Now, I use this model, okay? Here you have the power, and I compute the mean square error on the trained set and on the test set. And we have exactly the same phenomena, which is an overfitting issue. It's clear? Here you have the test set in orange and a blue, the MS mean square error on the trained set in blue. And if you exceed a polynomial order of degree 7, then you have an overfitting issue. Okay. So the overfitting is the fact that when you increase the model complexity, you will increase the variance of your forecast. And even if you decrease the bias in sample, you will increase the variance of your forecast, and you will, as the variance of your forecast will increase on the new data set, you will have a higher error. And so there is a link between the complexity and the overfitting, and now we have to fix what is the best complexity. And for that, we will control the complexity with what we call some hyperparameters. And we will use a method which is called cross-validation to determine the optimal complexity of my model and to avoid the overfitting issue. Any question? No. Okay, so understand the link between hyperparameters and overfitting, define what we call hyperparameters, understand the principle of the cross-validation, understand all doubt cross-validation. There are many types of cross-validation and the careful cross-validation. So first, what is an hyperparameter in machine learning? So in machine learning, you have some parameters and some hyperparameters. Hyperparameters correspond to the tuning parameters of the machine learning, or the parameters that determine the form of the model. Okay. The parameters characterize the form of the hypothesis, for instance, the threshold in the tree, okay, and the hyperparameters control the form of the model. Let me go back to my polynomial regression. I have y is equal to a0 plus a1 x plus ap x to the power p. What we call an hyperparameters is simply the degree of your polynomial. It controls for the forms, for the general form of your specification of your model. And what we call parameters, it simply corresponds to, for instance, to the parameters of your regression, A0, A1, AP. So the hyperparameters determine the form of the hypothesis of the model, and the parameters determine value of the form of the hypothesis. In general, the hyperparameters control for the complexity of the model, and as the complexity of the model determines the overfitting issue, the potential for overfitting issue, this is a major source of operational risk in the implementation of machine learning. Okay, because if I use hyperparameters which are not being well calibrated or well determined, well tuned according to, for instance, a cross-validation approach, then I have the risk to have a model which is too complex or not, or and to have an overfitting issue, or on the contrary, to have a model which is not sufficiently complex to reduce the bias of the model and to get a good predictive power. But in general, it is easy to understand that there is a problem when you have a model which is not sufficiently complex, okay? But it's more difficult to understand that you have an overfitting issue, okay? And so the hyperparameters help to control for the risk of model overfitting. So for instance, this is a type of hyperparameters and parameters for different machine learning algorithm. But okay, at this stage, I consider that you don't know what are these algorithms. So I will go back later when I will present you the tree or the boosting method to say, okay, we have to calibrate or to fine tune the dip of the tree, the minimum of the PR leaf, which are the hyperparameters that control the complexity of a decision tree. And then I let the algorithm determine the variables that are used in the model and the threshold used in each split. I will discuss this point later. Okay. So maybe you don't know what is a decision tree, but okay, this is a representation of the decision tree, whatever. This is a classification or regression decision tree. On the left, we have a tree with the depth is set to 2. Okay, we have and we have a very simple model. And on the right, we have a model is set to 10. And because I can explain you in tomorrow the link between the depth of the tree and the complexity. But if you consider a model on the left with a depth equal to 2, we obtain a model in which, for instance, we can predict a maximum of 4 different values. Okay, so why? I will produce some forecasts with 4 different values. And in my decision tree, I have some decision nodes, for instance, here, etc. And in each node, I use a feature, so an explanatory variable. And at the maximum, I use only 3 different variables. So x1, x2, x3. That's it. So I have a model in which I use 3 variables, x1, x2, x3, among all the variables that I've introduced in my Excel file. Okay, the algorithm, I've considered 3 of them. And given these 3 variables, it produces some forecast on Y, and the forecast on Y can take only 4 different values. If I increase the depth to 10, the complexity of the model becomes very different because the number of possible prediction climbs to 1024. Okay, so forecast of Y can take 124 different values. And the model can consider, this is not always the case, but this is the maximum of variables that it can consider, 1023 different variables. Okay. And just by controlling the size of the tree, you control for the complexity, the number of variables, the number of parameters that have been estimated, etc. So this is another table, for instance, that define the hyperparameters that are most used. For instance, here for a decision tree, in general, we control the max depth of the tree, maximum depth of the tree. But there are also criteria that can control for the complexity of models that can be considered as hyperparameters. We will see this point tomorrow. So what is the link between the complexity? So there is a link between complexity and overfitting. And there is also a link between hyperparameters and complexity. And so the hyperparameters are the way to control for overfitting. Okay, so what is the idea? We have, if we represent predictive error with a model complexity, the error on the test set, the error on the training data set, the error on the training data set always decreases, the error on the test set decreases and then increases. And our goal is to determine here an optimal or ideal range for model complexity. And the idea is to determine, for instance, the lag order, the polynomial order, my polynomial regression, the depth of the tree in my decision tree, or whatever in the random forest, the number of bagging model, etc. Whatever, the optimal value of the parameters that allows me to get the optimal complexity, model complexity. Okay. How to determine the optimal complexity with the hyperparameters? There are many ways to do that, but the most well-known method is what we call the cross-validation. The idea is to fix the value of the hyperparameters, such as to control the risk of overfitting. And the cross-validation is a statistical method used to evaluate the performance of a machine learning model. There are many variants for the cross-validation, the hold out, the scaffold, and the leave one out method. I will just discuss the two first, hold out and scaffold. In few minutes, in few words, what is the hold out validation? I split my training data set into 2 subsets. The proper training data set on which I will train my model, and the validation data set on which I will compute for instance, my R squared, my MSE, whatever. So give me a value of the hyperparameters. For instance, I consider a lag polynomial of order 3. I train the model here. If I summarize. Okay, let us imagine that I start with a polynomial of order 2. Okay. I train my model here. So I estimate the parameter A0, A1, A2. Okay. Then I compute the MSE here, given that P is equal to 2. Then I produce some forecast here, and with this forecast, I produce my MSE. I compute my MSE. Then I do the same with P is equal to 3. I estimate A1, A2, A3. I produce some forecast with this new model on the validation set. And then I compute my MSE with P is equal to 3. And what is the objective? The objective is to find the optimal polynomial order P star such that on this out of sample validation set, I obtain the minimum MSE. Because I am in the same configuration as if I consider a test set, so a new data set. I validate my model, I assess the performance of my model on a subset for which was not being used to train the model. It's clear? If you have understood, the the idea will be the same. So let me go back to my cross-validation holdout. Okay, this is the first method of cross-validation, so the holdout. So random division of the entire sample into 3 subsamples: the training dataset, the validation dataset, and the test dataset. Remember that at the end, if you remember well, sorry. Okay, at the end, we will assess our model with the optimal polynomial order on the test set. Okay, so we split our sample, our proper training, a validation data set. We will search for the optimal specification with these 2 data sets, and then we will compute the performance metrics on the test set. Okay, let me go back to the holdout. So in general, for instance, training corresponds to 50% of the observation, 25% for the validation, 25% for the test. We consider different values of the hyperparameters. For instance, the optimal, the lag order of my polynomial. So I consider theta 1, theta 2, theta L, for instance, P is equal to 2, P is equal to 3. I train my ML model on the trained data set. I deduce my model, H hat. I evaluate the prediction error on the validation sample. So this is for all the observation of the validation sample, the difference. So for instance, if this is MSE between the true value of Y and the predicted outcome of my model. This gives me what we call the cross-validation error. It can be the MSE, the R square, what you want, okay? The cross-validation error, but it depends on the value of theta. Then, what is the optimal value of my hyperparameters? It corresponds to the value theta star of my optimal parameters, hyperparameters that minimize the cross-validation error on the validation set. Then I know that, for instance, P star is equal to 3. I train the final model with the optimal value of the hyperparameters on the train and validation data set. So I use, remember, I have the train data set, the validation data set, and here the test data set. At the end, I use all this data to estimate my model. Okay? And then I use the test data set to compute my R squared or my MSE or what you want to compare my model to other model, etc. This is clear for, do you have some question about this holdout cross-validation process? Great. Yes, Fatme.
Excuse me, I'm a bit confused. Are hyperparameters defined by the user or are they defined by the machine?
Okay, very good question. The parameters will be determined by the machine, by the algorithm. The hyperparameters will be determined by a cross-validation method that you will propose to the algorithm because the algorithm, for instance, on scikit-learn, if you use a package of Python, you will have some values of the hyperparameters that you have to choose. Or if you don't want to choose these values, they will fix by a default value, okay? But in general, we fine-tune this value to obtain the most appropriate model with the optimal complexity to avoid overfitting. So I understand your point or your question. Your question is the fact that, okay, we speak about machine learning, and in fact, we have to find or to fix some hyperparameters. Yes, this is machine learning. So this is an algorithm, for instance. Let me go back to my decision tree, okay? I fix the optimal parameters with the cross-validation. So I will say to Python that, okay, you will use my decision tree with a max depth of 7. Okay?
Okay.
Because I use this procedure or train and validation to determine the optimal value. Okay? Then when you will use here, determine the optimal model with an hyperparameters fixed to 7. So Python will determine the optimal tree. So we choose the variables that enter in the tree. We'll determine the split values for these variables. So all this part will be determined by the machine. Okay.
Okay.
But I have a control on the general behavior of the algorithm. Okay.
Okay. Thank you.
Okay. So let me summarize. But this is what we have done. We have a training data set that is split in proper train, in which we determine the estimated model, and then we determine on the validation set what is predictive performance conditionally to fixing a value of the hyperparameters, and then we determine the optimal value of the hyperparameters. And at the end, we will use these two parts of the data set to estimate a final model, and this final model will be evaluated on the test set. Okay, you understand that? Okay, this idea to split the train and the validation is exactly the same idea that to split what we call before the train and the test. Okay, this is exactly the same idea. We evaluate here the model to determine the optimal hyperparameters. So if you have understood the holdout cross-validation technique, you will understand the careful cross-validation. So let me go back here The problem with the holdout is the fact that you determine once for all what is the training and what is the validation. And the idea of the scaffold is to consider all the data here and to use them alternatively as a training data and or as a validation data. Okay. And this avoids the fact that, for instance, you have a particular data in the training or particular data in the validation, and to have a particular diagnostic. Okay. So let me illustrate what is a cross-validation scaffold. So you divide your original training sample into K subsample. For instance, in general, we say K is equal to 5 or K is equal to 10. Okay. One of the scaffold is selected as a validation set. Okay, so I have 5 parts of my sample. And I select so 1, 2, 3, 4, and 5. And I select, for instance, this one as validation sample. The K-1 folds, other folds, constitute the training set. So I will train my model here and evaluate here on the last fold. We compute performance measure R-squared GNR, you see, from the data of the fold selected as validation test. So I can compute, for instance, here the MSE. Okay. And then all this operation is repeated by selecting another validation sample from the predefined fold. For instance, in the second loop of my algorithm, I will use the fold number 4 as a validation fold. So I will train my model on fold 1, 2, 3, and 5 and evaluate the mean square error on the fold of the data of fold 4, etc., etc. Okay. At the end, we obtain capital K performance score, 1 per fold, and we consider the mean of the K performance score, and we compute for this is there is a loop also on the value of the hyperparameters, so it's very time consuming, okay, because you have a loop on theta, you have the loop of the K fold, etc. And for each fold, you compute the error, and you determine the value of the optimal parameters that minimize the value of your mean square error, for instance, or cross-validation error on the K folds. So let me summarize. So I have a loop here with capital K iterations. I consider the first fold as a validation sample. I use the fold 2 to 5 to train the model. I compute my MSE here, MSE1, given theta. Then I consider the second fold as a validation sample. I use the other for the to train the model, and I have my MSE2 of theta, etc., etc. Given this procedure, all the data I've been considering is the validation, and all the data I've also been considering the training sample. And then I compute an average performance, which is, for instance, average MSE obtained over the 5 folds. Then I have a second loop over all the value of theta. For instance, this is my polynomial order, so we consider 2, 3, 4, 5 to theta L. And then I determine theta star, which is the argument that minimizes my MSE. It's clear? So it's time consuming. Be careful with the cross-validation. If I increase capital K here, I increase a lot the number of evaluation of my model, etc. But it can be very time consuming because I have to estimate many models, okay, each time. Okay, but this is a way to properly control for the overfitting and to determine the optimal value of the hyperparameters. This is another idea. Here we have the test set, and here you have the training data set that are used with a 5-fold cross-validation approach. At the end, you have the theta star. Theta star, okay, you estimate the model with all the training data set, and then you evaluate this model on the test set. This is the final evaluation here, okay? So let me summarize the cross-validation careful. Partition the whole sample into two subsamples, the training and the test, for instance, 70-30%. Partition the training set detrain into capital fold, K folds of equal size. D1 train, DK train. For given value of the hyperparameters, we train the machine learning model on all the folds except the K1. So we exclude the block D train K. We compute the model. We evaluate the prediction error on the excluded fold. So this is the excluded fold, and we compute the cross-validation error. Then we have a loop on the fold, and we average the cross-validation error over all the K folds, and we have a cross-validation error obtained by K folds. And the optimal value of the hyperparameters are the value of the hyperparameters that minimize the cross-validation error. Final model with a theta star with the optimal value is obtained by training the algorithm on all the training data set, and then you use a test set to compute your R squared, whatever, with other model. Okay. I insist a lot on this point because, okay, we will discuss tomorrow with, okay, let me go back here, for instance, okay, on this with Python, on the way to, it's really easy to make a cross-validation, but okay, you have to understand why you have this type of overfitting issue, and then to make a cross-validation, because sometimes people do cross-validation, but they don't want really understand why they do cross-validation. Okay, and sorry, up, okay. You will discuss this point later with a validation. Sorry, it is in French. I will change this evening the terminology, but this is a K fold with 5-fold. Okay, next year. Okay. So let me summarize a general approach for the validation. So you have the data set, which is split in test sets for the which is only used for the final evaluation. Your training data set is used for the cross validation, and you fix not the parameters but the hyper parameters. This is important to distinguish parameters and hyperparameters. You find the optimal hyperparameters. This gives you the optimal model, and then you will evaluate this optimal model with a test data set. It's clear? Great. This comes from scikit-learn, which is a package that we will use for machine learning. Okay. So key concept, you know what is hyperparameters, and you now know how to distinguish them from parameters. You understand that there is a link between the complexity and the hyperparameters, and there is a link between the complexity and the overfitting. So the hyperparameters allow you to control for the overfitting. You have a training. Sorry, this is not learning, but training. Okay. Training, validation, and test sample. Okay, for the K holdout approach. This is a cross-validation, okay, for determining the optimal reuse the hyperparameters, and two well-known methods are holdout and the K-fold approach. I gave you the name of a third approach, which is the cross-validation, which is, okay, I gave you a third name, which is leave one out cross-validation. Just one idea. This is the same idea of the K-fold, except that we leave 1 point here. So the fold corresponds to 1 point. We consider n-1 individual in the training data set, and then we evaluate the model only for one observation, and then we have a loop over the n individuals to, okay. What is the main problem with the leave one out cross-validation approach? Do you have an idea?
I think it will be the same as the holdout cross-validation, that maybe this one have some particular observation features or.
Yes, no, it's not the problem because, okay, you have a loop, so you consider all the data set as validated, all the points of the individual in your data set as a validation sample, okay? So even if I have a particular or specific individual at each point, when I will consider the average of the cross-validation error for all the individuals, okay, there is no risk to have we have a robust evaluation of the cross-validation error. But no, the problem is the fact that we have a loop for n individuals. For instance, if I have a data set with 3 million of firms, then we will run or train 3 million of model by changing only one observation in the training data set each time, okay? And don't forget that we have another loop for all the theta values. Okay, so it's very time consuming. Okay, so in general, we don't consider leave one out cross validation approach. Okay, so I propose to run a short count just to check if before to okay, sorry, excuse me. I propose to keep the second section for the next section. So the next section is about classification and regression tree. So tomorrow we'll see a particular algorithm and we will discuss all this question of hyperparameters, parameters, etc. cross-validation within a given specific algorithm. But this evening I propose to stop here and to run a count just to check if everybody has globally understood what is the main concept that of this first part of the lecture. So you see my yes, you see my screen. Okay, so for people who don't know what is count, so you type count here, sorry, count with KHOOT, and you have two links, kout.it and kout.com. So you click on kout.it here, and you will find this type of screen in which you have to enter a PIN code. And the PIN code is the following. You can also use a QR code here to log yourself to the count. And for people who don't know, with Scout is just a website that allows to make some quiz just to check, okay, if you have understood the main ideas of the first part of the lecture. And you have to introduce a pseudo.
Sorry, I have a question.
Yes.
For a k-fold method, why we dividing the sample to 5 or 10 only? Why we don't divide it by 7 or 8?
Yes. I don't know why 5 or 10. Okay. Just what is the general perspective? The general perspective, if you increase capital K, it increases a lot the computing time. Okay, this is a general rule. Then how to? I don't know why we have rules of thumb in machine learning that consist in considering 5 or 10 folds. I don't know. Okay, but this is a practice. I don't have a precise idea of why there is if there is a justification. I'm not sure that there is a justification. It's just a practice. Okay. But if you want to
You can try 7, for example.
yes, yes, there is no problem. Okay, you will fix the value of K and the cross-validation approach.
Okay, thank you.
Is there other question? No. Okay, before to launch the Kahoot quiz, so first there is no no particular difficulty, just to check if you have understood the basic concept and retain the vocabulary. So and you have time to answer. The timer is about 20 or 30 seconds per question. So, okay, I have 21 participants. I don't know if it is okay, 20, so that's someone. I let 1 minute before to start the count. Okay, 21. 20, someone has some difficulty. Propose to start. Okay. So there is no trap, no trick, no problem. Very simple question. Okay, I don't search for a very complicated answer. Let's go. Okay, let me. Let's go. True or false? Artificial intelligence is a subfield of machine learning. Yes, this is false. Alors, vrai en franc, vrai is true and false is faux is false. Okay, sorry, it is in French. Machine learning is a subfield of AI and not the contrary. Quiz, what type of learning is not part of machine learning? Indeed, natural language processing in general is considered as is not considered as a subfield of machine learning, because in general we have machine learning NLP techniques that allow you to consider text, and then you transform the text with these techniques into a vector or feature or label, and then you use machine learning technique to make some prediction. Okay. True or false? Supervised learning requires label data. True. Supervised learning, label data, unsupervised learning, unlabeled data. True or false? Semi-supervised learning requires label and unlabeled data. It is true, semi-supervised learning requires both label and unlabeled data. True or false? The bias measures the dispersion of model forecasts. Great, this is false. This is a variance that measures dispersion of a model forecast. True or false? The squared error is a sum of the bias and the squared variance. This is false. This is the sum of the squared bias plus the variance. Okay. This is the bias which is expressed in introduced as a squared in the squared error. When the complexity of a model is increased, there is only one good answer. Great. The bias decreases because the bias, we consider the bias in sample. Okay, and so there is, when you increase the model complexity, the bias mechanically decreases. Okay. True or false? The risk of overfitting decreases with the complexity of a model. It is false indeed. As you observe on my graph, my figures, you see that, okay, what we call an overfitting is the fact that, okay, your error, for instance, measured with the MEC, R squared, whatever, increases on the test set and decreases on the training data set. And this divergence between the result of the performance of your model on training and test set is called an overfitting issue. Last question. In case of overfitting, the model presents great low bias on the train set and high variance on the test set. Great. Congratulations to Khaled, Aya, and Shiraz. Great, but whatever the podium, I consider that overall you have understood the main concept of this first part, which was devoted to the definition. So it is very easy. And so now tomorrow, given this definition, we'll enter in detail and in the first algorithm. And then next week, we will enter in detail in the ensemble method, and we will apply in parallel with Python, starting from tomorrow. Do you have any question? No. So no question. So see you tomorrow for the second session devoted to this decision tree.